I would like to welcome you on this new chapter where we are going to talk about C++20 modules. Modules are the last piece of the puzzle in what we covered in terms of C++20. It is one of the big features in C++20. We have already seen concepts, ranges, coroutines, and modules are going to be the main topic of this chapter. One of the main points in C++20 modules is to change the compilation model of C++ program. In all the C++ before C++20, we used to highly depend on headers to define things that we could include in other files and get our code to be reused. That way of doing things has a lot of benefits as time has proven, but it also has a lot of drawbacks, and C++20 modules were conceived to try and address those issues. One of the big points in C++20 modules is that you get tight control over what is exported from your module or what is not exported. So if you want a function to be visible, you export it. If you don't want it to be visible, you keep it inside your module, and users of your modules won't be able to see it. That's something you don't get by default if you use the old header-based compilation model for C++. Now, in the old days, you would have a header file. Here we have the math.h header file, and we would include it in a bunch of C++ files. When you get to compile your program, the first step would be for the preprocessor to take the content of this math header and paste it wherever it is included. And this would result in the same code being processed multiple times, hurting your performance in terms of compilation speed. And C++20 modules try to improve on this, as we are about to see. The header-based compilation model has a few problems. We have talked about compilation speed, but we also have ODR violations. If a header file is included multiple times, there are chances that the same definition is going to show up multiple times. This would cause a bunch of errors. There are cases where they include order matters and causes different behaviors for your program, and this is a headache if you happen to come across this problem. And as we have seen, headers don't offer encapsulation out of the box. Here is a piece of code that shows one of the problems you face if you use the header-based compilation model. And the problem is that a file you include has the capability to change the behavior of your program. Here we have a define. This is a preprocessor define. We are defining a macro here. And down here, you see that we have a piece of logic that does different things based on whether we have this variable here or this macro here defined. If it is defined, we run this piece of code. If it is not defined, we run this piece of code. And depending on what includes this macro here, your code is going to do different things. And this may be really bad. And C++20 modules avoid this problem in that macros are not allowed to be exported outside modules. So if I import a module, its macros won't be affecting what is happening in this file that imports a module. This is one of the problems that C++20 modules try to address as well. Here is an illustration of the same piece of code we saw before, but now we want to assume that we are using C++20 modules. The same idea applies really. We have the code in the module and we are including the same code in different CPP files, but the way C++20 modules work, a module file is not going to be processed multiple times. A module file is going to be compiled into a binary form, and any file that imports that module is going to be referencing that binary code. So we will process the module code once and get a binary form, and this binary will be used wherever this module is needed. So we don't have to process the module code to generate binary multiple times, and this is going to improve your compilation speeds. Try to think about cases where we have to include the same header maybe 20 times, 100 times. This is going to really make your builds fast. And there are some people that already report huge improvements in compilation speeds for very large projects. Now, if you use modules, compilation speed is going to be improved by the BMI, as we have seen. ODR violations are going to go away because declarations are confined inside the module. The The include order problem is going to go away because the module is available in some pre-compiled binary format, and it is going to be included immediately where it is needed in your application. Another big benefit is that declarations are well encapsulated and you have tight control over what is exported and what isn't. Now that we have a few basics about modules, let's look at the actual structure of a module file. Your module file is going to start with this module thing, module semicolon. You really need this thing. And if you go down, you will have a module declaration. The syntax is going to be export module, and you specify the module name. Here, the module name is print. This is something you need to keep in your mind. And after your module declaration, you will have what we call a module preamble. The module preamble is where you put your import statements. In this case, we are importing the string header and IO stream. And after the preamble, you have the module purview, which is the meat of what makes your module. In this case, it is just a function, but it could really be any entity in C++. It could be a function, it could be a class, it could be a concept, it could really be anything. And as we go forward in the chapter, I will show you different ways you can use all those entities in the C++ 20 modules mindset, if I can say it like that. So a module file has three parts. The global module fragment is what is inside this module thing and the module declaration. In the global module fragment, you will have your includes, and yes, it is possible to still use the old header-based includes like we do here if it doesn't already support being imported like this, and I will show you a few examples of this. But now what I want you to focus on is the three parts that make up your module file: a global module fragment, the module preamble, and the module preview. Inside the global module fragment, you will have your includes or any other preprocessor macros. In the preamble, you have your import statements, and the module preview is what makes up the meat of your module. If you look down here, you see that we are exporting this print method function here. And this is what I meant when I said that anything you need exported outside the module needs to be explicitly exported. If you don't export this function, it won't be visible outside. If you want it to be visible, you have to explicitly export it like we are doing here. Okay, here are a few facts about the global module fragment. It can only contain preprocessor directives. It allows to include stuff the old way, and it is recommended to put your include statements in the global module fragment. If you put them elsewhere, you will face a few errors, and it is recommended to put them in the global module fragment. That's the idea here. The preamble is going to be containing your import statements, and the purview is going to contain the meat of the module: functions, types, classes, concepts, and really any other entities that you want to make up your module. Here are a few points I want you to keep in mind as we go forward. Each module is going to be compiled independently into an object file. So each module is a translation unit, and this is fairly different from what we are used to in old C++, where a header is really not a translation unit. Headers are included in the translation units. In C++ 20 modules, a header or a module is a translation unit, and it is compiled independently. Modules must be compiled in an order in such way that all the dependencies are compiled first. So if a module is used by other modules, the one that is used by other modules has to be compiled first. If you are compiling manually on the command line yourself, you have to take care of this order yourself. And this is a really big headache if you have a big project. That's why we have to rely on tools like build systems IDEs to help us in taking care of these dependencies. In practice, you will be using IDEs and build systems to figure out this order automatically. Another thing I want to cover here is the extension that modules use. This is a confusing point if you ask me. In C++ 20 modules, I would really have liked it if they had one extension for modules across all compilers, but in practice, every compiler is going to have its own preferences. If you are using the Visual C++ compiler from Microsoft, module files will have the IXX extension, the BMIs will have the IFC extension, and implementation files are going to have the CPP extension. This is the practice or the recommendations that we have to follow if we are using this compiler here. It is possible to use other extensions and tell the compiler to treat those as module files, but that's another step, and it would really help if we had good defaults that are supported across all compilers. If you are using GCC, GCC doesn't really enforce any extension. In many examples I have seen the CC extension. Clang has also its preferences. Module files will have the .cppm extension. Implementation files will have the CPP extension. And the BMIs will have the PCM extension. And we will get a chance to see this when we play with modules in a while. In this chapter, we will be using the IXX extension across all our compilers. And implementation files will be using the CPP extension. We will make sure to instruct our compiler to treat IXX files as C++ module files, and we will do that by passing special compiler options to GCC and Clang. This will allow us to compile the same source code across all compilers that we are interested in this course, and those happen to be Visual C++, Clang, and GCC. Now, before we head off and try to use these concepts in practice, I want to introduce header units. Header units are a concept we have to try and use existing headers as module files. For example, in old C++, we are used to the IO stream header, we are used to the vector header. In module code, some people introduced the idea of being able to include these things or import these things as modules in C++ 20 modules. And a header unit is produced when your compiler tries to take an old header and compile it in a way that it will be treated as a C++ modules. They are part of an effort to make it easy to put all the code to modules. The compiler is going to compile the header into a form where it can be treated like a module. This is what we just said. And if you have used precompiled headers in old C++ code, the idea is the same. They are precompiled in a way that we can treat them as modules. In this chapter, we will try to use the import keyword as much as we can, but sometimes that's not going to be possible because compiler support isn't there yet for C++ 20 modules, and you will see what we can achieve. The goal I have here in this chapter is to be able to compile the same code across all compilers. That means that sometimes we will avoid the good module practices to try and comply with what the weakest of our compilers support. So we will see more of this as we progress. Don't worry if this is not making sense yet. And where needed, we will revert back to including the old way in the global module fragment. Because of how groundbreaking C++ 20 modules are, for them to work properly, it's not up to the compiler only. We also need good module support in terms of the build system and the IDE. And at this point, the IDE from Microsoft Visual Studio, is the best when it comes to providing a good module experience. They have good IntelliSense, they have good support for the IDE, and everything feels natural. That's what I will be using to show you how to edit and compile modules. But once we have the code edited, we have the ability to compile the code using any other compiler of our choice. So I will show you how to also compile using GCC and Clang. Okay, the main compilers we are interested in are GCC, Clang, and Visual C++. In this course, I will be using GCC 13.20. It is what I get from WinLibs, as I have shown in the install videos. I would recommend you get the latest version. I will also show you how to use Clang 18. This is the latest version I can get of Clang, but this is going to be living in a Docker container. Don't worry if you don't want to use Docker. We will also show you how to use the Clang compiler coming from WinLibs. But in terms of Clang, you need at least Clang 16 for what we need to do in this chapter to work. So if you can't get it installed on your local system, if it is difficult for whatever reason, I would recommend trying out this Docker container. It is really great, and it gives you the latest features in terms of this Clang compiler. We will also show you how to use the Visual C++ compiler from Microsoft. And if you happen to want to use Docker, here are a few facts you need to be aware of. Here is a piece of documentation you can read to see how to use the Clang compiler with C++ modules. This is where I got the Docker image that I used, and I will be using the latest Visual C++ compiler and the Microsoft Visual C++ compiler. So these are the tools that I will be using to edit and compile my code here. If you want to use Docker, please make sure you have a good understanding of Docker. This is not a course about Docker. I will be showing you how to use it to compile C++. But if you really need to learn Docker, I would recommend doing more research in that regard. But I will give you a few pointers if you want to do what we do in the course. To be able to use Docker, you need to install it. So go to your browser and use your favorite search engine and see how to install the Docker engine. Once you have the Docker engine, you will pull the image. This is how you pull it. I will show you these things in a minute when we get to do them. You will need to change to the location of where your files are stored. In my case, it was in this sandbox folder. And you will need to run the Docker container. This is how I run it. And this V flag allows you to match the current folder in your host machine to a folder inside the Docker container. Once you have the Docker container, you attach a terminal to it and you can start running the commands that we will be running in this chapter here. Here is a fact I want you to take a moment to read. If it doesn't make sense, keep it in the back of your mind. This mainly comes from the fact that the name of the file where the module lives may be different from the name of the module. And Clang seems to expect the output PCM file to be the same name as the module name, but we will be using this flag to tell Clang to produce the name that we want in terms of the PCM BMI file. Again, don't worry if this sounds confusing. At this point, I want to try and run some module code and show you the tools that we will be using in this chapter here. Let's start with the Visual Studio editor. So I will open it, and the code that we will be using in this chapter is going to be coming from the course repository. So go there, go to this chapter, and you will find this code. I am going to click on Introduction here and open the code for this chapter or this lecture in the chapter. And you notice that we have two files. We have a math.ixx and a main CPP file. The math.ixx file is our module file. So this is what we will create in our project. And we have the main file that contains the entry point of our application. In each of these folders, I will also provide a README file, which is going to give you instructions on how to compile the code. At this point, I will show you how to use the Visual C++ compiler, GCC 13.20, Clang 16 that I have access to from WinLibs on my Windows machine, and Clang 18 coming from the Docker container. So make sure you have this code. It is going to be what we use in this chapter here. Once you have Visual Studio, we will create a new project. So create a new project. It's going to be a console application, and we will choose the location of this. Let's change this to go somewhere we want to go. So we need to go for me, it is going to be sandbox, and go to 49 modules. This is going to be the folder where my projects are going to be stored. And I will specify the name of the project to be the same as from my GitHub repository. So let's come back here and put in the name of the project. It's going to be 48.1. And I want to place the solution and the project in the same directory. And this means that this is going to be the full path of the project as shown here. Once you have what you like, click Create. This is going to create a project for you. It's going to be a blank C++ project. And the first thing I want to do is to rename this to main.cpp and clean up the code here. I think we don't need all this junk. So and we want to import IOStream because we are using modules. So import IOStream. We don't use include anymore. And for this to work, you need to enable C++20 for this project. This IDE is going to be using C++14 or 17 by default. So let's enable C++20. You do that by clicking on the project here, right-clicking, go to Properties, choose C and C++, go to Language, and choose C++ Language Standard to be C++20. Once you have this, I also want you to go to General on top here and select Scan Sources for Module Dependencies. Here you will select Yes and click Apply and click OK. And now our project is ready to start using C++20 modules. If you go back to the GitHub repository, you will see that what I just did is described in these instructions for the Visual C++ compiler. So if you are ever confused, make sure to come back to this README file and read about it. I will be putting it in this folder when I push to GitHub for this course here. So let's try to compile. We can do that. So build the solution and see what we get. You see that build succeeded, one failed. Why is that? We don't have a closing curly brace here. So let's make sure we have it and build again. Now the build is good. We can debug, start without debugging, and this is going to say hello world. Let's create a module file. Now that we have a project ready for C++20 modules, you create a module by coming to the project, right click and hit add and say new item. And if you do that, you will be given the option to create a C++ module interface unit. This is what Microsoft calls them. It doesn't really matter. Ours is going to be called math.ixx, and we add it to our project. And we have seen the structure of a module file, but I would recommend even coming to GitHub and copying our math.ixx file here. You see, it is the same code we saw in the slides really. So you can click here to copy raw file and come back to our IDE, take out everything and paste in our module code. So we have our module thing, we have our module declaration. Here I want you to see that it is possible to name the file containing the module and the module differently. This is something I do a lot for my own personal reasons, and I thought I should show you this if it happens to make a difference for whatever it is you are trying to build. So here is our global module fragment. Here is our module preamble, which is going to contain our imports. And down below, we have our module purview. Once we have a module, we can use it to do all kinds of crazy things. For example, because we are exporting this function, we want to call it where this module is imported. Now that we have the module, we can import it. We don't need to import IOStream at this point. We want to import math, and we want to call this say something function here. So let's do that, say something. Okay, once we do that and try to build, let's build a solution and see if it works. Could not find module math. What could be going? It's not called math. You see what I did here? It's called my math module. Okay, so I need to go in the main file and provide the name of the module. What you import is not the name of the file, is the name of the module. And this was an error, but it was a lucky one because I get to emphasize this for you. Otherwise, some of you would have made the same mistakes. So import my math module. This is what we import. Once we have this import here, we will have access to anything that is exported from this module file. Now that we have this, we can try and build. Okay, if you get 1 succeeded, 0 failed, it means your compilation was successful and you can try and run this. So debug and start without debugging. And we have saying something, which is what we printed in our say something function here. Now, notice that we are importing IOStream. This is what is called a header unit. This is what C++20 provides to be able to use old headers in C++ as modules. This is not always going to work on all compilers, but the idea is that they should work, and we should expect this to work when we have good support for modules across all compilers. Now we have compiled our module code using the Visual C++ compiler. It is possible to do this on the terminal, but I thought it was a waste of effort because we can do this easily through the IDE. If you are on Windows, I would recommend using Microsoft Visual Studio at least to edit your module code. Because you can see that we don't have a lot of errors, IntelliSense is there, it really provides a good experience. But if you are on another operating system, don't be discouraged. You can still type your code and compile it on the terminal as I am about to show you. If we go back to our README file in this lecture here, you will see that we can also use GCC 13. This is what I get from WinLibs. So let's go there and say WinLibs. And if I go there, if you remember from the install section, this is what we used as our compiler. It provides GCC 13.2.0 at this point, and it also provides Clang 16.06. I have this installed on my local system, so from the Visual Studio editor, I can come to View and do Terminal. This is going to open a PowerShell window for me to use right inside this editor here. Okay, we have PowerShell here. I can say G++ version, and it is going to show me which version I have installed, 13.2.0. I can even ask the Clang version I have installed, and it is going to give me the version here. So you need Clang 16 to be able to do what we want to do here. And I would recommend getting the latest version of GCC you can. If you are on Windows, you can use WinLibs like we are doing here. So let's go back to our Git repository and see how we can use GCC. You see the input files are still what we had before. We have the IO stream header unit that we need to compile before we compile any other thing. But we also have math.ixx and main CPP as the input. If you go where our project is stored, where is it stored? Let's go there. Okay, introduction. You see that we have a lot of noise coming from the Visual Studio editor, but the main thing really is the main CPP file and the math.ixx file. And in this case, we will try to compile directly using the G++ compiler. Let's grab the command here. I don't want to type it because I may do errors and have typos that waste our time here. Let's do ls to show the content. You see we have the main CPP file and the math.ixx file. This is what we are interested in, and the rest here is really noise that Visual Studio uses to set up this project for us here. But now we can compile the main CPP file and the interface file. With the GCC, the first thing you have to do is to compile the header unit. So let's do that. We copied the command from GitHub earlier. This is the command g++ fmodules-ts. You tell it that you are compiling a C++ system header, and you specify the header that you want to compile. Once you hit enter, this is going to generate a BMI for the IO stream header. And if you do ls, you see that we have generated a GCM cache folder here, and this is what is going to contain your BMIs. Let's go and grab the other command. So we can grab the other command, which is going to compile our interface file. So let's put that here. And if we do that, this is going to also compile this interface file. And you see that we have an object file as a result of running that command. And the last command is going to link our executable. And the executable is going to be named rooster.exe. So let's paste the command in here. And if we do ls, you see that we have a rooster.exe file. If we run it, it is going to say saying something. And we have successfully compiled our module code using C++ 20 modules through the GCC compiler. If you want to use Clang, again, I provided these instructions that you can follow. This is the Clang version that we have on Windows. But on Windows, I couldn't use PowerShell, and I resolved to using the command prompt for this to work properly. Let's try to use PowerShell and show you the problem that I got. So let's copy this, okay, for Clang. Before we do any further compilation on the terminal, we should remove the noise that we introduced. Let's remove any object files that we generated. And let's remove the GCM cache folder, and also remove rooster because we don't need it. And we will try to use the instructions here to compile with Clang. Let's copy the command as we did earlier. try to compile. Okay, this is going to try and compile the IO stream header, okay, as a header unit. The same idea we had for GCC ready. This is going to run. It's going to give you a warning. This is because Clang is really in experimental support for this. Don't worry about this warning at this point. Once we have the header compiled, we will try to compile the IXX file. Let's talk about the command a bit. Here you see that we are using C++20. We will tell it the location of the IO stream BMI that we just compiled, and we will tell Clang to treat any IXX extension files as C++ modules. This is what this command here does. We will tell it to compile and output a file named mymathmodule.pcm. And if you come back to our code, let's open Visual Studio. You see that the module file is named math.ixx, but the module is named mymathmodule. Clang expects all BMIs to be exported in the name of the module. That's why we are using this name to output our PCM for our module here. This is something you need to keep in mind if you are using Clang. So let's copy the command and put it in our editor and see what we get. So copy, and let's paste this. So this is going to compile our PCM, and you notice that it is saying no such file or directory PCM. This is the problem you face if you try to use the Clang compiler in PowerShell on the Windows system. But this is going to work if you use the terminal. So let's clean up whatever we just generated here. So let's do ls and see what we have. We have a PCM file here that we don't want, that was generated earlier. So let's remove any PCM files, and we want to start a terminal window. Let's start a developer prompt, okay, which is going to allow us to run the commands for Clang here. So let's do that. We will start over and use the first command to generate our header unit. So we can paste this in. It is going to generate our BMI. Let's go back and grab the second command. We put that in here, and it is going to compile. You see that we have no error. This means that our PCM was generated. And if you go in here and do dir, because we are on the command prompt, you will have our mymathmodule PCM file generated. Let's go back and grab the third command, which is going to compile our main CPP file into an object file. So go back to the editor and hit the command. We grab another command and compile to generate an object file for our module. So let's do that. Paste and run. If we do dir, we will have our object files, and all that remains is to link everything together and create an object file which is named rooster. Let's do that. We can come back to our terminal and hit this, and if we do dir, we should have our output file named rooster. If we run it, it is going to saying something, and we have just successfully compiled our module code using the Clang compiler on Windows. I will also show you how to use the Docker container because I can. I really like this because it gives me access to the latest compilers, but if you don't want to go through Docker, you can do what we have just done in this chapter here. But if you happen to be on a system where it is inconvenient to install or build the latest compiler for yourself, you can use Docker. It is really going to give you access to the best tools here. So what do we do to use Docker? The first thing you have to do is to install the Docker engine on your system. So make sure you have it installed. If you don't know how to install it, you can go to your browser and say install Docker, and you will have a bunch of results here. You can go through this, install it on your system. Once you have it installed, you will be able to go to your terminal, whatever really. So let's use developer PowerShell here and say Docker version. It is going to show you the Docker version once you have this installed. After you have it installed, you will need to pull the Docker image. And what we want to use is this Docker image here, Clang Ubuntu, and we want to pull the tag for 18. So let's go to Docker Hub, where you pull Docker images from. So let's do Docker Hub, and let's search for Tix99. I think that's the name of the user, Tix99. So Tix99 Clang Ubuntu. Okay, I think this is the container. Once you are here, you can pull this container and use it. You see they have a bunch of tags. They have 18, which was pushed 21 days ago. You can see this is really new. Yeah, you can use it if you need the latest Clang. Once you have Docker Engine installed on your local system, you can pull this image and use it. And we even have a command here you can copy to pull it. I have it already pulled, so I don't need to pull it again. But if I paste that command here, you can see that it is saying docker pull tix clang ubuntu 18, which is exactly what I showed you in the slides. So you pull it. Once you have it pulled, I would recommend changing to the location where you have your project. In this case, I changed to the dsandbox folder because I have a lot of things installed there that I want to manipulate through my Docker container. Once you have a location you like, you will run this command here. Let's show it in big format so that you can really see it. You say docker container run, and you will specify the name of your Docker container. In this case, it's Clang, and I specified hack because I watch a lot of Breaking Bad. You specify a flag to say that it is interactive, and the v flag here is going to map a local folder to a folder inside the container. In this case, the pw command is going to pick the location where I am, and it is going to map to a location inside the container, which is home Gakwaya in this case. After that, I specified the name of the container that I want to run. Again, this is not a course about Docker, so I just show you the commands that I use on Windows. This may be different on Linux or a Mac, especially on this command here. So if this gives you problems, please check and do more research on how to make this work on your operating system. Once you have this running, you can attach a terminal to the Docker container. In my case, I have Docker installed and I already have pulled this image. So what I can do is Docker container LSA to show the images and containers that I have. You can see that I have Clang Ubuntu. It is the same container that I just talked about. And I can start it. I start it by saying Docker container start and specify the name of the container, which happens to be Clang Hank here. So Clang Hank, and I start it. It is started. Once I have it started, I'm going to attach this terminal to it. And I do that with Docker container attach Clang Hank. And once I do that, I am inside the container on this terminal here. If I do uname A, you see it is a Linux box that I have access to from inside Microsoft Visual Studio, and this is really cool. So let's change to home Gakwaya, the directory that I mapped. And I mapped this because it contains all of the projects I want to play with in this container here. Let's change to the C++ 20 masterclass, the source code for this chapter here. And let's do ls to find the code, cd 49 to go to our chapter here, and do ls cd 48.1 for the introduction here. And if I go there, I have access to everything inside the project that we are working on inside Microsoft Visual Studio here. Let's do lsalh to see everything. You see we have our Visual Studio files. We also have a few things earlier from building with Clang on Windows. Let's take out all this noise except for the Visual Studio project because we are still using this inside Microsoft Visual Studio. So we can remove any object files, and we can remove rooster, and we can remove any PCM files, PCM. And if we do it lsalh, we will see that we have the main files of interest for this project here, the main CPP file and the math.ixx file. Even if we are working inside the container, we are still manipulating these files here, and this is really cool. Okay, now that we have this, we can run the commands to compile inside Docker. You see, it is the same thing as we did for Clang 16, but because we are on Linux, we are making sure to use the C++ standard library that comes with Clang. This is what this flag here does. The rest is really the same. So let's grab the command and copy it and put it inside our container. Hit enter. This is going to compile our header unit. Let's grab the next command. And again, I will share this file as a resource to this lecture, so you can copy these commands and use them as I am using them here. Don't worry about typing all these because you may introduce typos that are going to eat a lot of your time. We have done this, so let's run the next command. This is going to compile our main file into an object file. So let's put this here. And we will grab the other command, which is going to compile our module file. So let's do that into an object file. If we do ls, we have our object files. And the last command is going to produce our binary. Let's copy this and put that in our terminal. And we hit this, and this is going to generate our rooster binary. On Linux, you run it like this, and it is going to say something exactly as we expected. And this is really all I wanted you to see in this lecture, giving you an overview of how you can compile your module code using the main compilers that we are interested in this chapter. We saw how we could use the Visual C++ compiler from Microsoft. We saw how we could use Clang, both 16 and 18. We used the 16 on Windows, and on Windows you have to be careful to use the terminal because it's going to give you an easier time. PowerShell has problems that I don't want to get into, and we saw how to use the GCC compiler. Now that you know this, we can head over in the next lecture and build our very first module file. Go ahead and finish up here and meet me there.